off of packet number 2, this is a mean value theorem problem. Are you okay with that, or you want to move forward? You want to go for it? Okay, all right, so mean value theorem. Okay, so here's the big picture with mean value theorem. We just want to be able to apply this formula here. F of B minus F of A over B minus A. So the first thing you want to do is, let's not worry about the derivative. Let's worry about finding the slope between the endpoints. So how do we find the slope between the endpoints? Any idea? Can we use the order pair somehow and the function somehow to do that? Yeah, let's find the order pairs first. Yeah, find the order pairs, and then we can worry about the slope. So f of 10 is just going to be root 10 minus 1. F of 50 is just going to be root 50 minus 1, ends up being 3 and 7, right? And then we can find the slope, right? Find the slope between the endpoints. Change in y over change in x. So what you get for slope? So 7 minus 1/10, okay. Yeah, there we go. So we have this part figured out. Now I need to figure out the derivative portion of it, right? I want to basically ask myself, this is a guaranteed slope. I want to know where on this curve is there a slope of 1/10. So I'm going to set the derivative equal to the slope. And then if I do that, I can figure out the location of this particular slope. So to find f prime, we're going to go through chain rule. Rewrite it as parentheses to the 1/2. Hey Tam, hey Pavan.
Hi.
Hi, Mr. Yang. How are you?
Good. We're just doing number 2 from packet number 2.
Sounds good.
Okay. Okay. So here's my derivative going through chain rule. Outsize derivative times insize derivative. Right. Parentheses to the 1/2. Inside is the x minus 1. So outsize derivative, I have 1/2, parentheses to the negative 1/2. Insize derivative times 1. I clean up my derivative, and I set it equal to the slope. So now I have the two pieces that I need with mean value theorem. I'm just going to set them equal to each other and try to solve for x. Okay, there's my derivative, there's my slope. Once I set them equal to each other, I'm figure out how can I get x by itself. So what if I cross multiply, right? Cross multiply, divide both sides by 2, square both sides. I get x minus 1 equals 25. Add 1 to both sides, I get 26. So I have my order, I have a part of my order pair. I know my slope, I know x is 26. So if I want to find the tangent line equation, the last missing piece that I need is the y value. All right, it says find the tangent line equation here. So how can I find the y value of the function? Okay, take 26 and do what with it? Right, let's plug it back into the original function, right? Because my order pair, if I give it an x, in return, it'll give me the y value. So 26 minus 1 is 25, root 25 is 5. Got my order pair, got my slope, and then point slope form. All right, does that make sense? Mean value theorem? If you see it on the exam, you'll know what to do. Okay.
I understand so far.
Good. You guys okay? Daniel, you okay? Okay. Okay. What about problem number 3? Are you guys okay with 3? This is implicit product rule problem.
Yeah, I'm good with that one.
You're good? Daniel, you good with that? Product implicit, okay. Number 4 is point of inflection. So you find first derivative, then you find second derivative, then you set equal to 0, find critical points, plot your second derivative sign line. If there's a change in sign, there's a point of inflection. You want to do it or you want to move on?
Actually, can we do that one?
Okay, all right, number 4. So point of inflection, we know we have to work our way to the second derivative. So we're going to find f prime and then find f double prime. But to find f prime, let's go ahead and bring the x squared and x cubed up so that we can avoid quotient rule. We can just rely on power rule instead. I thought I did this one earlier. Let's see. Okay, so here's number 4. Let's go ahead and let's get this set up so that we can find the derivative easier. I'll rewrite it as x to the negative 2 minus x to the negative 3, right? It's a lot easier doing power rule from here than it is from this point. So let's find y prime. And then once we get to y prime, we'll find y double prime. And y double prime is going to be where we're going to start looking for critical points and therefore potential points of inflection. Okay, so y prime, go through power rule. All right, keep going. All right, what's next? How do we find critical points?
Do we factor first?
Yeah, we could. Yeah, we can factor. So 6x to the negative 5. So I'm left with x minus 2. Yeah, that works. Set both equal to 0. Okay, this may give us some trouble here. We get x to the negative 5, divide both sides by 6, I get 0. 1 over x to the 5th is equal to 0. Okay, we know that's never true. So nothing here. The only critical point that we're going to be able to find is at 2. So we need to confirm that this is a point of inflection. So we're going to create a second derivative sign line and see if there's a change in sign from one concavity to the next. So I'll choose 1 and 3. We can plug it into second derivative. 6 times 1 to the negative 5 is still positive. Positive times negative is negative. Plug 3 in, 6 times 3 to the negative 5. That's going to be a really small decimal number, but still positive. Times 3 minus 2, which is positive. So multiply 2 positive, we still get a positive. So yes, point of inflection because there's a change in sign. Okay, next page. Tell me if you want to do this one or skip it. Number 8, limit problem. You can do either L'Hopital's or you can do conjugate method. What do you guys think? You want to do it or you want to skip it? Do it, okay. So the first thing we do with limits is we always plug in the real number. So I'm going to plug 1 in. Okay, so if I plug 1 in, I get 0 over 0. So once I have 0 over 0, I know there's a hole, and I got to keep working with the problem. So I can go through the conjugate method, which is multiply the top and bottom by the conjugate. So what's my conjugate term of the numerator here? Okay. Same expression, I just changed the what? Just changed the sign, right? Okay, so now we're going to FOIL this out, but when you FOIL this out, you're only going to expand the numerator because the denominator is going to be already prepared for you to cancel out. Okay, so expand. Root x times root x is just going to be x. Middle terms drop out. Negative 1 times 1 is minus 1. Factors cancel out. We reevaluate. And we get 1 over square root of 1 plus 1, which is 2, 1/2. Okay, so that's one method to do it. Do you know another method to handle this type of problem? Okay, with limits, if you get 0 over 0, you also have another option, and that's L'Hopital's rule. And this is where we can find a derivative of the numerator and derivative of the denominator, reevaluate, and we should get the same answer. So either way works. But you got to first plug in, right? You got to have a 0 over 0 before you can jump into all this conclusion. So I'm going to prepare my numerator ready for power rule. Okay, so my derivative, I'll put LH to indicate I'm going to apply L'Hopital's rule. 1/2 x to the negative 1/2 is my derivative using power rule. The negative 1 goes away. And then denominator, we find the derivative of that separately. So x becomes 1. So now that we have a different form, we can reevaluate, plug 1 in for x. And that's the same thing as 1/2. So either L'Hopital's rule or conjugate method, and you get the same answer.
And just to make sure, L'Hopital's rule is only when we have a 0 over 0 hole, right?
That's right. Yeah, you got it. That's why we always plug in first to gather information before we jump to conclusion, right? We got to have 0 over 0 before we know that this method is going to work out.
Okay, thank you.
Okay, good with 8. Number 9, find the maximum value. This is extreme value theorem. So this is where you find a derivative, find the critical points, see if the critical points lands between the endpoints, and then you plug your endpoints and your critical points back into the function, compare y values, and highest y values your absolute max, lowest y values your absolute min. You guys want to see number 9 or move on? Move on. You guys okay? Hmm?
To do problems like number 9, can you repeat what you were saying?
Okay, yeah, so this is extreme value theorem. So this is where we find critical points. So you set the derivative equal to 0, find the critical point, and then test a critical point and the endpoint into the original function, and then compare their y values. Highest y value is your absolute max. Lowest y value is your absolute min.
All right.
Yeah. So you're good with that?
Yeah.
Okay, good. All right, so this one is more implicit, and then using the x value to find the slope, and then find the slope, then plug in 1 to get the order pair, and then point slope. I'm sorry, no, this is just finding the slope. So plug 1 into the function to get the y value, and then implicit, plug in the x and y value to get the slope, and then your slope is your answer. Number 11, equation of tangent line. I need to find, I have my point, I need to find my slope. So to find slope, I have to find the derivative. To find the derivative, I have to use which method to get to the derivative here? 2x plus 3 over 3x minus 2. This is a quotient rule, right? So quotient rule, plug in the order pair, get the slope, and then point slope form. Okay, take a look at 12. 12 is implicit. 13, average rate of change. All this means is just find the slope. That's all it is. Find the slope between the endpoints. $14 is another L'Hopital's rule problem. I would say 12 is implicit. Okay. How does 12 through 14 look to you? You guys good? Move on. Okay. This is a chain rule. You got the outside, inside, and inner function. I think we saw this recently on the quiz. Hmm?
The chart that we had as well.
What do you mean the chart? Derivative chart. Okay. Yeah, this is remember the outside, inside, inner part, and then find the derivative.
Yeah, I was thinking differentiation, like derivative and subchart.
Oh, okay. This one is a little bit more complex. I don't think you'll see one as messy as this one, but this is a little bit of chain and product. Yeah, second page looks okay. Next page. Okay, this one, number 20. Any idea what's required to find the derivative of x raised to the ln of x? Okay, so look at how this is set up here. This is a variable raised to a variable. So how do we handle a variable raised to a variable? Do you guys remember? Okay. It's not power rule, it's not chain rule, it's not a to the u. There's a very specific method of handling these types of problems. Okay, and that method is log differentiation. We don't have a rule that can handle this part of this setup, so we got to go through log differentiation. So we'll take the natural log of both sides so that we can allow that exponent to come down in front. So now this exponent is free to move in front. Okay, so now I can go through product rule to handle the right side, and the left side is a little bit of implicit. Okay, so 1 over y dy dx. F prime g plus f g prime. Remember the rule for natural log of x is u prime over u. So let's see what this ends up being. F prime is 1 over x times the g function back to f g prime. Multiply the y over to the right side. Natural log of x. And then what can I replace y with? Not dy dx.
Oh, wait, no.
Do we have a substitute for y? Very beginning, right? Original equation.
Oh, yeah, x to the power of x.
Mm-hmm. Combine these like terms together, I get 2 ln of x over x. And this is answer choice C. Okay. Let's look at 27. This is a derivative graph. I think it'd be good for us to practice that. Danny, you want to take the sheet?
What's the electric equation sheet?
Hmm?
No.
He just wants to see the work. Okay, so 27, what we're given is the derivative graph. We want to know what the original graph looks like. So derivative graph, understand what we're dealing with. Above and below the x-axis means slope behavior of the graph. Above the x-axis is positive slope, below is negative slope, and on the x-axis is slope 0. So if we create a slope sine line, we can kind of have some idea as to how the graph is rising and falling. So we know that critical points is at -1 and 1. Above translates to positive slope. Below translates to negative slope. Above, positive slope. So we want the graph to look like this. We want it to rise to relative max at -1. We want it to fall to a relative min at 1 and rise again. So maybe a graph that looks something like this. I'm sorry, we want relative max at -1 and relative min at 1. So we want to rise to some y value, fall to some y value, and rise again. So I'm just making my graph follow the path of the arrows, matching my answer choice. Looks like my best fit is B, right? Let me skip through here. Number 34. How about a let's see. How about a related rates problem? I'll do a related rates problem. Okay. About 52. All right, cone problem here.
Can we do this one?
Yeah, this one here, 52.
Mm-hmm.
Yeah, so this is we gotta do similar triangles. Okay, so 52. I know I can just go ahead and create my triangle within the triangle. Radius, height, 4 and 6. Yeah, my dimension is not too form here. This should be longer and this would be shorter. Okay. We have our volume formula, which is pi over 3 r squared h. This will be given to you. We know that we can create proportions between radius of the water level is to the radius of the container, as the height of the water level is to the height of the container. And cross multiply. Okay, let's gather some more information here. We have a cone reservoir, diameter 12, height 4. Water is flowing into the tank at a constant rate of 10 cubic feet. If water is flowing in, we know that volume is increasing and it's a rate. So you know it's a dV over dt. Okay, at the instant when the surface of the water is 2 feet above the vertex, so that's the height, the water level is rising, so we're looking for dH dt. So this information kind of gives us a hint, right? We know that we want h's in our equation because when we find the derivative, we want these things to pop up so that we can solve for them. So that tells us that we want, ideally, the fastest path to our answer is to get that r to be replaced, get that r to be removed. So I'm going to solve for r here. So divide both sides by 4. I get r is equal to 3h over 2, right? You can reduce both sides by, divide both sides by 2, I get 3h over 2. So now I can take my 3h over 2 and I can dump it into the r here. So we'll let this go in place of that, in the hopes that we can get a volume equation with just h's and not any, and so that the r's can disappear. Okay, so here's my updated volume equation. Pi over 3 r squared, so 3h over 2 squared, and then times h. Okay, clean this up here. Square everything we see here. I get 9 pi over 12, which reduces to be 3 pi over 4. And then combine the h's together, I get h cubed. So now we can move into our derivative, right? Every variable is going to be hit by time. So v will become dv dt, h will become dh dt. Keep the coefficients. H cubed becomes 3h squared. And then we attach dh dt. All right, any questions so far about the process and the steps that I'm taking here? So from here, we're able to make it down to here. Okay, replace dv dt with 10, replace h with 2, and then we can work our way down to dh dt. Right? This combines. This cleans up a little bit here. Just 9 pi actually. The 4's cancel out. And then divide both sides by 9 pi. Careful, the pi is going to stay in the denominator. It's not going to move up. Feet per minute. It's asking for decimal value, so it ends up being, in the calculator, ends up closest to 0.354. So this packet doesn't have everything in it. So I want to ask if you want to see a particular type of problem, I can always find one for you and we can work it out. So again, here are the topics. You got limits. L'Hopital's rule is tied into that. Continuity conditions. Derivatives. Tangent lines. Particle motion. Creating velocity sign line. We did this in class today. Continuous differentiable piecewise function. Related rates. Volume, surface area, cone, similar triangle. We did linear approximation. We just highlighted EVT and we did a mean value theorem. Rolle's theorem is pretty similar. It's just that we know that f of a has to equal to f of b. First derivative tests, concavity sign line, derivative rules involving trig, arc trig, logs, and exponentials. Expanding logs, log differentiation, derivative inverse at a point, interpreting derivative graphs. We just did one of those. So yeah, I know Bhavan and Tam, you guys are 7th period, so you guys have an exam tomorrow. So is there any problem that you want to see or any concepts you want to see? Or you can continue working through them and I can answer those questions tomorrow because I'll have a help session tomorrow morning as well. But if you have anything right now, I can go over that as well.
Nothing right now.
You okay? Bhavan, how about you?
Yeah, same with me. I think I'll probably practice 1 or 2 more.
Okay, so you have access to all the packets. I would, we did packets 1 and 2, so I would tonight go over packet 3, organize your information, right, get all that ready, and then if you have any questions, you can also send me a message tonight. I can I can provide some feedback if you have questions about any of the problems. All right, good luck with your studies. I'll see you tomorrow.
Thank you very much.
Yeah, sure.
Thank you, Mr. Green.
All right,
Thank
see
you.
you, Thomas.
So if we don't have our exam tomorrow, do we need to come?
We still have class tomorrow.
We do?
Mhm.
Do you think school will be shut down?
Why? Is that what it
there's like
said?
a ton of people in quarantine for their own COVID.
Yeah, I don't know. I guess, if it is, then I'm sure we'll get an email.
Also, it's chances.
Yeah. If it is, then we'll find out soon enough. All right, see you. Bye, Thomas.